This video I want to talk about something I'm doing with reservoir computing, and I added some details that I think are necessary to understand how this thing works. I'm going to start with this video here I upload to YouTube probably a couple years ago, in which I solved the problem of computing or predicting the solution of a dynamical system using dynamic mode decomposition. And the model for this system is described here with these equations. So there is a bunch of equations. And the variable that I am interested is in this concentration here. So this system is solved numerically, and in particular I take the concentration, and then I construct a DMD model for this variable. And it turned out that the model that I constructed based on a superposition of DMD modes turned out to be quite good. This is the solution that I got. The solution is here. So now I'm going to use the same solution. I'm going to use the same solution for this breather. I'm going to play the video a little bit. Yes, the solution is running here. I'm going to use the same solution to construct now the prediction for this same model, but now using reservoir computing. And first, I think I need to explain how the reservoir computer works. This is a very simple diagram found in this video. So this person here, Daniel Gothier, is the author of this paper here in this article in Chaos. Let me see if this person is the other one. No, it's this one here. This paper here. This is the author of this paper. And this is an article from Nature in 2021, I guess. Yes. So I'm going back to the diagram here. So this is quite simple. We start with a signal. It could be a multi-dimensional signal. It could be, for instance, a sinusoidal signal. And then we use that function as the input signal for this network. This input signal is going to be processed into the reservoir. And once I get a collection of the total number of states, then I'm going to use this collection of states to compute a matrix of output weights. Now, how to specifically write or construct the reservoir computing? I found another paper, this one here, in which they explain how this reservoir computing should be prepared. So we start by initializing the reservoir computing. I'm going to explain what that means in a little bit later. Then we train the reservoir computing, which is the diagram that I just showed, and we are going to collect the corresponding activation states. Then we use this matrix of activation states in the third point here to compute these output weights. To construct these output weights, we are going to use a ridge regularization, which basically means that we want to minimize the error between this y and the prediction. That's all we need to do. So let me see if I have some other scheme to show here. I think, yes, I have another scheme here. This is a simplification of the reservoir computing, how it works. So we take an input signal, and we combine this input signal with the state of the reservoir computing at the present time step, which is going to come from a previous time step. And then with that, we are going to compute the activations of the states at the present time. We are going then to collect this new state into a matrix of states, which describe the reservoir. Once I have collected all the states for all the for each one of the time steps, then I'm going to use this aggregation of states to solve this expression here. This expression, what it does basically is just minimize the error between the predictions here. This is the matrix of states and the weights of the output layer with the output. So we want to minimize this error here. We need to add some regularization to prevent overfitting, but the best way to understand why we need this lambda parameter here is because, as you can see in this expression, this is the solution of the regularization, of the minimization process. This matrix here, S transpose S, often is singular. So that means that we cannot find this inverse for this operation here. So that's why we need to add some regularization there. What else is here? This is the process for training. We run a input signal and we run it for all the elements in the input signal. We construct this pre-activation for each one of the states, and we are going to use a nonlinear activation function. In particular, we use a hyperbolical tangent, and with that we compute the state of the new time step. Then we are going to aggregate everything into this big matrix of states. This is the matrix of states of the reservoir, and then we solve the regularization. I wrote this in here. This is the problem that we want to solve for the training of the reservoir computing. Again, we want to minimize this error, and we add this regularization here. So basically, what we do is the usual thing. We derivate this expression equal to 0. Then we solve the resulting expression for W out, and this is the result is going to be, let me check, what is the result here. So one more time, we need to add this regularization process, this regularization constant, to prevent this matrix S, transpose S, from being singular. So now I'm going to the code. I'm going to show how everything works in the code. So here I am defining the initial state of the system. So probably the interesting thing to point out here is two things. One is that the matrix of weights in the reservoir is very sparse, very sparse. So I am using a sparsity of 0.1. So I initiate this matrix as a full dense matrix, but then later on I apply a mask. So for instance, in this case, this is sparsity 0.1. So when this expression is true, then in this particular case it's 0.1. So 90% of the elements of the mask are going to be larger than this sparsity. So in that case, W is going to be 0. So essentially, this means that 90% of the weights are 0. And very important, this is constant. Once I initiate the system at the beginning of the process, I keep these values. The only thing that I'm going to train, the only weights that I'm going to change are for the output layer. So this is the initialization. I'm going to go to this fitting process. This is what I just mentioned at the beginning. So I introduce an input signal, and I'm going to run this loop for all the elements in the input signal. Then I'm going to apply this update of the reservoir, which basically this means to apply a um, nonlinear activation function for the combination of the input signal and the state, the current state of the reservoir computing. I'm going to apply this activation function. Then I compute the new state of the system, and then I'm going to pass this state of the system into this part of the code. And basically, I'm just going to collect all the states into a big matrix. So notice the difference. This is a state. This is an individual state for the current state of the system, and this is aggregated into a states matrix. So this states contains all the aggregation of the partial states. So this is the fitting. What else? And then here is the operation to compute the W out. So this operation here essentially is what is written previously here, this expression here. So this is, let me see again. So S transpose S plus lambda. So S transpose S, and then the regularization. This is lambda, and this is a identity matrix. Okay, so that's it. And with that, I finished the training of the network. And then the prediction. The prediction is just this operation here. Yes, this operation here, this dot product, is W out multiplied by the state. That's it. So I'm going to use this process. And here I have a very simple example. I think I'm going to run this code to show how it works. This is super simple. I'm going to do a little bit more complicated, but just to show how this thing works, I'm going to run this thing first. So in this example, I am using a sinusoidal wave, very simple. And the values the values of the signal and the prediction are almost the same. So I'm just going to zoom here to show that there are actually two different things. Let me go back again. I'm going to zoom somewhere here. Oh, it's difficult to see. That are actually two different. Yes, I think you can see here. Okay. Now, I need to modify these are the errors. The errors are ordered 10 to the minus 7. I'm going to modify this code first to compute the prediction, not just of one sinusoidal wave at one location, but of the entire domain. So I had to do several changes here, but the most important that I didn't mention previously is that this new reservoir computing network is going to have now more input signals, one for each location on the domain. I made already the changes, so I am just going to show how this thing works for this simple case. As again, it is the same sinusoidal wave, but now on the entire domain. And still, the real data and the prediction are almost identical to one another. Prediction, actual data, and then I think I compute, this is the errors. So prediction minus the true value, and then square. 10 to the minus 6. So it's a nice error. This is another representation of the error. So by the way, there is a factor here. It should be 10 to the minus 8 factor here. And this is the animation of the real, the actual data and the predictions. So now what I'm going to do is use this code. I already made all the necessary changes, and I'm just going to run the same code, but for the data containing the breather, the one-dimensional breather that I used previously using dynamic mode decomposition. Now I'm going to use the same data to compute the prediction using reservoir computing. So let me see another. This is I have to change here the number of inputs. And this is how many inputs I have in the for the breather. I am also increasing the size of the reservoir from 100 to 200 because this system is bigger, so I need a larger reservoir. What else do I need to change? I think I need to modify this limit here. And the same for the surface of errors. Let me see what it is here. Yes, this new the array of the solution is very big, so I'm just going to plot every 10 time steps to make this, to plot this thing a little faster. So I am also going to plot every 10 units. What else? I think that's it. I don't think I have to do any other change. Okay, let's run this thing to see what happens. Okay, no errors. So it's a little bit difficult to see here the details because this is thousands of time steps. So I'm going to show better the three-dimensional version. Okay. Actual data and prediction looks almost the same. So this is why I wrote the calculation of the errors to be able to distinguish, to tell something about the prediction. Oh, the errors are so small. I'm going to change this axis here. I need to change, so otherwise we don't see anything. So let me change that and run it one more time. So by the way, as you can see, this thing runs super fast. I'm running this on a small laptop and it still runs super fast. I'm going to change here, this limit here, and maybe I need to change also in the surface. Let's see. Yeah, let's try changing the limit there. And then running again. Okay, so I'm going to close this because we cannot see. I mean, there is the solution is there, but it's difficult to see in this representation. But because there are so many time steps, so I'm just going to zoom this area here to show. See, so that's the breather is there, and the prediction the same. So the breather is right there. So the prediction and the actual data are almost the same. I'm going to see one more time the three-dimensional representation of the solution here. Position, time, and this is the amplitude. Close this thing to show the errors. Now we can see the errors. It's about 10 to the minus 3. Okay. There is another, this is the surface of the errors. Okay. So as you can see, most of the errors are located in the central part where the breather is evolving. On the borders there are not too many changes, and that's why there is no too much error on the boundaries. So again, there is a factor here, should be 10 to the minus 3 in this case. And finally, prediction and the data are almost the same. So that's it. That's all I wanted to show. Here I I extract a bunch of measurements of errors, the mean square error and the infinite norm. All these values are small for this case. So just let me, before finishing, let me see if I wanted to show something else. I think that's it. Um, ah, this is, I don't know if I show this, but I am just going to uh, briefly summarize how to use a reservoir computing. So we initiate the reservoir computing, then we run it using the training input. The input signal in this case was either the sinusoidal wave or the breather data. And we collect each one of the new states into a big uh, matrix of activation for the total reservoir. And with this big matrix S, we are going to compute W out by minimizing the error between the uh, prediction and the output. We are going to do this minimization by using this expression here. And we need this regularization parameter there. And finally, once we train the reservoir computing, then we are ready uh, to do predictions. So this book here, I'm going to show is this one here. This book is from 2012, I think. Let me see if I have something else to show. No, I think that's it. That's all I wanted to show for the reservoir computing.